Alright guys, so in this section we're going to be discussing some application problems using the trigonometry that we've learned so far. We've already been doing some basic applications, solving for one side of the right triangle or the other, given an angle and another side. So we're going to go back to those, and now that we know how to do inverse trigonometric functions, we should be able to solve even more application problems now. Okay, so here we have our first example. We have a ladder that is 16 feet long, leans against the side of a house. The angle of elevation of the ladder is 80 degrees. Find the height from the top of the ladder to the ground. So when we don't have a sketch or a diagram, it's always helpful to sketch a diagram of what the problem is saying. So let's try to draw the triangle that represents what's going on in this problem. So we have the right triangle here, and let's say the building is here on the right side, and we have an angle of elevation. The ladder is right here. The angle of elevation is 80 degrees. And the ladder itself is 16 feet long. And we want to find the height from the top of the ladder to the ground. So how far is this ladder reaching in this building? I'll call it h, or height. So let's figure out what that h is. And we've seen this kind of problem before, where we have one side of the triangle, and then we're asked to find another side, and we're given an angle, right? If we had the second side here, the adjacent side, we would use the Pythagorean theorem and just find that h. But we don't have that, so we need to use a trig here. So we ask ourselves, what trig function of 80 degrees would put 16 and h together? And the answer is sine or cosecant. But again, we want to try to do the first three if possible, since those are the ones that we have right away in the calculator. So we want to set it up by saying sine of 80 degrees is equal to opposite, which is h, over hypotenuse, over 16. And then we solve for h. H is going to be equal to 16 sine of 80 degrees, and this is just calculator. Okay, so putting this in the calculator, we're gonna get that. First of all, we want to make sure our mode is in degrees, since we're dealing with degrees here in application problems. We want to change that to degrees and then plug it in, right? So we have 16 sine of 80 degrees. This is already in degrees, so it'll understand that 80 is degrees, and then we'll get 15.8 if we round to one place. And this is feet, by the way, guys. So don't forget your units here. Here's another example, maybe a little bit more involved here. We have it at 0.65 feet from the base of a church. The angles of elevation to the bottom of the steeple and the top of the steeple are 35 degrees and 43 degrees respectively. Find the height of the steeple. So again, let's try to graph a picture of what's going on here. Let's say we have the church there, and on top of it, we have the steeple right there. Okay, so we're trying to figure out the height of this steeple right here. So I'm going to call that h. So remember, this is the building. So we're going to pretend this is the building of the church. On top of it is the steeple, and we're given the angles here. The angle to the bottom of the steeple is 35 degrees. This angle is 35 degrees right there. And this one, the bigger one, the angle of elevation to the top of the steeple is 43 degrees. And of course, we have our 90-degree angle there. Okay, so how do we find h here? And now keep in mind that this triangle here is not a right triangle. This one, this big one is, this little one here. And we have two angles here, right? So if we're going to use our trig functions, we need to have a right triangle here. The problem is that we don't have this rest of the side. So it looks like we're going to need this side x here. Let's start with the smaller right triangle here. So we have that. And by the way, guys, forgot one thing here. 65 feet from the base of the church. This is the base of the church. So 65 feet from there would be right here. So we have that side, right? We needed that side there. So we can now set it up. What trig function with respect to these angles here, respect to those angles, put the 65 and this side together where the h is. So let's look at the smaller right triangle first. Tangent is the one that's going to bring these two sides together. So tangent at 35 degrees is going to be equal to x divided by 65. So notice how you can solve for x here and have x equal to 65 times tangent of 35 degrees. Now we can put this in the calculator and get a value, but I'm just going to keep it in the exact form right here for right now. and set up the other equation. Okay, so now we can set up the other equation here. We have the tangent of 43 degrees is equal to, same idea, h plus x all over 65. Now we can cross multiply here and solve for h, and we're going to end up with h plus x is equal to 65 tangent of 43 degrees. And then obviously we can subtract dx and move it to the other side, and we'll get 65 times tangent of 43 degrees minus x. And we already have x over here, so we're going to go ahead and plug that in, and we'll have h is equal to 65 tangent of 43 degrees minus 65 tangent of 35 degrees. Now the rest is just calculator, so we go ahead and put in our calculators here. We have tangent, or 65 first, 65 times tangent 40, and remember I've already changed my mode to degrees, so make sure you keep it in degrees, minus 65 times tangent of 35 degrees. We hit enter. Let's see, height is equal to 15.1 feet. Okay, another problem here we have is going to ask us to find the angle now. So here's where our inverse trigonometric functions are going to come in handy. As always, let's get a sketch of the graph, a sketch of what's going on here. We have that from the time a small plane, airplane, is 100 feet high and 1,600 ground feet from its landing runway, plane descends in a straight line to the runway. Determine the angle of descent in degrees of the plane. Okay, so again, let's get the picture. Let's get the picture of what's going on. We have an airplane here, and it's going to descend this way. And this, guys, by the way, is in no by any means up to scale. So this is just to give us the idea of what's going on. But we have, let's pretend this height is going to be 100 feet, and the ground distance from the landing is 16 feet. Let's assume this is our landing runway right here, and the airplane starting to descend at the point where it's 100 feet high. And we want to find the angle of descent. Now you want to make sure that you know where the angle of descent is. Yeah, sometimes it's confusing, and you may think it's the one formed with the vertical, but the angle of descent is actually going to be this angle right here. Okay, so I'm going to call that theta, which is equivalent of saying if you have the horizontal line of sight of the airplane there, the angle of descent would be right there. So the point is that when we're talking about angles of depression or angles of elevation, the angle is always formed off of the horizontal, whatever that may be. It may be the ground, or it could be the line of sight. It's always going to be off of the horizontal, not the vertical. So once we have our angle in place, then we're going to set this up, right? So notice this is the first time we are doing a problem where we're not given the angle, and in fact that's the very thing we're trying to find. But we have two sides though, okay? We don't care about the length of the other side, the hypotenuse. That's not important in this problem. But we have the other two sides, so there's no point of doing Pythagorean theorem to find the other side. We need to find theta. Okay, so to do that, we're going to use tangent of theta. And the reason I use tangent is because I have the opposite and the adjacent side, right? And if we set it up, we get 100 divided by 1,600. Now, of course, you can simplify that if you like, but this is equal to 1/16. You want to look at it that way. Tangent of theta is 1/16, but that's not the answer. We want to find theta. So this is where you're going to use your inverse trig. Taking tangent inverse on both sides here, theta is going to be equal tangent inverse of this 1/16. And now this we're going to put in the calculator. And since we want the answers in degrees, remember we already have our calculator change or in degree mode, so we can go ahead and just use our tangent inverse here. We're going to do second tangent, which gives you the tangent inverse of 1/16. And again, since you want your answer in degrees, you want to make sure your mode is in degrees so that your answer is in degrees. And there it is. Your answer is going to be, and let's round it to just one decimal place here, 3.6. So this angle of descent is 3.6 degrees roughly. Okay, so notice how to find the angle, we are now going to be using our inverse trigonometric functions, right, to undo the process and be able to find those angles there. Okay, so here's a problem with bearings and directions. So we're gonna have to get a good sketch of the graph here of what's going on and be able to understand the terms here. So let's get right to it. A sailboat leaves a pier heading due west at 8 knots. After 15 minutes, the sailboat changes course to 16 degrees northwest at 10 knots. Find the sailboat's bearing and distance from the pier after 12 minutes on its course. Okay, so let's try to get the picture here. First of all, let's make sure everybody understands that knots stands for nautical miles per hour. So in other words, it's representing speed here, and we're going to get our distances from that. Okay guys, so here we have a rough sketch of what's going on. So if we pretend this is the pier here, right here is the pier, and this is where the sailboat is leaving from, and it goes, it's the problem says heads due west at 8 knots. And remember, 8 knots is miles, nautical miles per hour. So if it went for 15 minutes, which is a quarter of an hour, then it really just went for, it traveled for 2 miles there, 2 nautical miles. So that's where that 2 comes from. And right at that point, after 15 minutes, it changes directions here and it gives you an angle of 16. So here, the important thing about this type of problems is that you know where to put the angle here so that you can get this picture right and ultimately the answer right. So the 16, every time you're dealing with bearings, right, direction and bearings, that angle is always going to be off of the vertical line. So don't get confused with the angles of depression and angles of elevation, right? Which they're typically off of the horizontal. Here is always off of the vertical. In other words, the north and south. If you look at north and south axis here, it's going to be the 16. So we're changing directions northwest. So northwest is in this direction, but the 16 is going to be right there. Not off of the horizontal, but off of the vertical. So one way to remember it or interpret this is to always read it, it's 16 degrees west of north. Now it's kind of backwards there, but it's always coming off north, either north or south. That way you make sure that it's always off of the vertical. So that's our angle, 16 degrees. And of course we know already this is 90 right here. And then it says it goes for 12 minutes in this direction, right, in this course at 10 knots. Now 12 minutes is 1/5 of an hour. So 1/5 of an hour, going 10 miles per hour, and 1/5 of an hour you would have gotten also 2 nautical miles here. So we have 2 and 2, and then we have this angle here. Okay, so the problem is asking us 2 things here. It wants us to find the sailboat's bearing and distance from the pier. So the pier was here where we started, and this is where it stopped. Once it changed course and traveled for 12 minutes, it stopped right there. So this distance right here, right? So what is this? I'm gonna call this D. And the bearing. Now remember, the bearings always come off of the vertical, so you're gonna have to figure out what angle we're talking about. Okay, is it this one inside the triangle or the one outside? Well, and again, if you remember how we do bearings, the bearing is going to be this right here. So I'm going to call that theta. Now, if we found this angle right here inside the triangle right there, we could easily figure out what theta is, which would be our answer here for the bearing, because this whole thing is 90 degrees. So that's going to be our goal now. All right, so there are many ways that you could solve this problem. You can play around with the geometry here, but one way that you could approach the problem here would be to, let's go ahead and trace, because this triangle here is not a right triangle, and we can, you know, cut this right here to make a right triangle, but we ultimately want to find this D here. So let's form a right triangle that has this D as a side. So if we just drop a perpendicular there and we extend this line, we'll have a right triangle there. Okay, now where that D is the hypotenuse now of this big triangle. Okay, so we're gonna have to find some things before we can find that D. Let's go ahead and call this X and Y here. All right, so let's go ahead and find this X and Y, and then it'll be easier to find D once we have this 2. So the first thing we want to do is look at this small right triangle here. We have this side, the hypotenuse of this small right triangle is 2. So we just need an angle. Since we have 16 here, this angle right here, the sum of the two has to be 90. This is gonna be 74 degrees. All right, with that 74, we should be able to find x and y. So let's go ahead and find x first, or either one. It doesn't matter. So for x, we'll set it up with the cosine. Cosine of 74 would be equal to x over 2. Cross multiply, x is equal to 2 cosine of 74 degrees. And that is roughly, we're going to compute that in the calculator. Okay, and again, make sure your calculator is still in degrees, as we're dealing with degrees, and we put that in the calculator, and we get 0.55. And these are now nautical miles. Remember, these are distance we're computing here. In the same way, we're going to find y. So we'll set it up with sine now. Sine of 74 degrees is equal to y over 2. Y is equal to 2 sine of 74 degrees. And in the calculator, we get this 1.92. And again, these are nautical miles here. So how do we find this angle here? And I'm going to call this just alpha. So then tangent of alpha would be equal to, and I'm going to use the letters first, opposite, which is the y, over adjacent, which would be x plus 2. I know that I calculated this x and y already, but these are approximations of these distances. So for the sake of avoiding rounding errors here, I'm going to plug in the exact thing here. Instead of using the numerical values that we found, I just did that here so that you get a sense of what they are. But to plug them in here, since we're going to have to do more rounding here, I'm going to use the exact thing the x and y are and put the whole thing in the calculator. So y is 2 sine of 74 degrees. And we're going to divide that by x, which is 2 cosine of 74 degrees, and then plus 2. So for alpha would be equal to the tangent inverse of this whole thing. So once we put that in the calculator, now we can round because, you know, we're going to have to get an angle there. Okay, so after putting it in the calculator, we get actually a nice 37 here, right? If I'm not mistaken. So doing tangent inverse of this whole thing here, this whole expression, and again, I did that so that I don't have to round in between. I'm using the exact values, and notice how I get a nice 37. If I had used these numbers right here, it might have given me, it would have been close enough, but it might have been like 36 point something or 37 point something because I rounded in between. So try to avoid doing that so that you'll get the most accurate answer at the end. So this would be a nice 37. And this was already in degrees, so 37 degrees. From here, now remember that 37 is not your bearing. Your bearing is going to be 90 degrees minus 37, right? If you look at here, the sum of the two, they're complementary angles. So this will have to be 53. Now, how do you write the bearing? Well, you say then bearing would be north 53 degrees west, and that will be your bearing. All right, so what's left here to do is just to find that distance d, but there's several ways that you can find that now. Since we have x and y, you can find the use of Pythagorean theorem. Really, you don't need to use any of the trig here. But let's use the trig just to practice anyways. We have this angle alpha now, and we have this whole side y, or this one here, but let's just use y, and we can use sine of alpha to find this d here. So we can set it up this way. Sine of alpha is equal to opposite, which is y, over hypotenuse, which is the d. We cross multiply. Now remember, we already have y, we already have alpha, and I'm going to put the exact values so that it gives me the most accurate solution. So we have y over sine of alpha, which plugging in our numbers would be, y was for us 2 sine of 74 degrees. This is over sine of 37. All right, so putting this in the calculator, we get roughly 3.2 nautical miles. All right, so there you have it, guys. So this problem was a little bit more involved. The most important thing here is to get the picture right at the beginning. Make sure you indicate the bearing correctly where it's supposed to go. You have the right orientations, and the rest is just trig. right? Being able to set it up. You may have to find different unknowns here to be able to find your answer, but once you get the idea and have the right diagram, the right sketch, you should be able to work it out. Okay guys, so one last application of our trigonometric functions is going to be harmonic motion. So the periodic nature of our trigonometric functions here, specifically sine and cosine, are going to help us describe the motion of a point or some object that vibrates, isolates, or rotates in that fashion, where its movement resembles a wave motion. So for example, consider this ball at the end of the spring. So the position at equilibrium here is the place where the ball is at rest here, right? You're not stretching or compressing the spring. So that's what we call the equilibrium state. So that's what you see here is 0 centimeters. And the displacement, which is going to be described by this amplitude here, this A, is going to be how far you can stretch the spring, or how far this ball can go in each direction, right? And the positive and the negative direction. So in the negative directions, when you stretch it, can go negative, right, or 10 centimeters that way. If you compress it, it goes 10 centimeters the other way in the positive direction. So that's going to be described by the amplitude here. So we can say this is the maximum displacement, and we already know that's our amplitude there. And the period of these functions are going to be, just like we know already, going to be calculated by 2 pi over this w here, this coefficient in front of the t. But in this context, the period is going to represent the time that it takes this ball to reach its maximum displacement below 0 all the way to the maximum displacement to above 0 and back. That would be one period, right? The end of one cycle. Now from here you're going to have also a frequency. So frequency is going to come from basically what the period is. So the frequency is going to be equal to the reciprocal of the period. And it basically represents how many cycles, or what portion of a cycle gets done in 1 unit of time, whether that's seconds or minutes or whatever the unit of time is in the problem. Okay guys, so here's an example. So we want to find the equation for simple harmonic motion here for d equal to 0 when t is equal to 0. Now notice how we had 2 equations here for harmonic motion, and it's either sine or cosine for us. So how are we going to determine which one it is? Since they're giving us that d, the function value here, d, which is the distance at a given point here in your displacement, is equal to 0 when t is 0. So at time 0, in other words, at the beginning, at rest, right, it's right at 0. So right here, right in the middle, at equilibrium. The only one that is going to give you 0 here is sine, because sine, when you plug in t for 0, sine of 0, you know, is already equal to 0. If you plug it in here, 0, cosine of 0 is going to give you 1, and times a would be whatever a is. So that's not going to give us 0. The only one that will give us 0 at equilibrium, right, when the distance is 0, so that means we're at right in the middle, right there at rest, at equilibrium, at time 0, is going to be sine. So right away, we know we're going to use that. D equal to a sine of this w, by the way, is called omega, lowercase omega. So we know it's going to be the sine function. So now we need to figure out 2 things, a and omega. So we're asked to write the equation of this simple harmonic motion. So it's going to be in terms of d and t, right? T for time and d for displacement. So we just need to find a and omega here, and then we'll be done. Now they give us the amplitude, so right away, remember the amplitude is the a. Right away we have amplitude here, which is the absolute value of a, is equal to 6. And the period, which for us is 2 pi over omega, is equal to 3 seconds. So then from here, we can find omega here and then plug it into our equation. So it's very straightforward here, guys. Now, the amplitude, you may say, well, how do we know if it's positive or negative 6 for the a? It will depend on whether the ball moves up first or moves down. Okay, guys, so here, solve for omega. Omega gives us 2 pi over 3, and then now we can write our equation here. D, the displacement of this ball or this object, is equal to 6 sine 2 pi over 3t. And that's it. That's our equation right there. Now again, the -6 or +6 will depend on whether the ball or the object initially moved up or down. Notice how you could also be given this equation, an equation like that, and be able to derive the amplitude or the displacement and the period from the equation would be the other way around. So this is another application where we can apply our trigonometric functions to describe a real application. In this case, sine and cosine can be used to describe simple harmonic motion.